Okay, so I think last time you told me that you wanted to look at problem 1 and 3. All right, so let's look at that. So let's see what is problem 2. I think I remember problem 1. I have no idea about problem 3, but it doesn't matter. We figure it out. So let's see exam 1. Where's exam 1? Here it is. Okay, if you want, you can go look at the solution or no solution. Doesn't matter. We have just the problem statement. Okay, so all right, so it looks like it's this figure over here that you need to determine the equation of motion. So let's see what they said. The pedal of the car can be modeled by the single degree of freedom shown in the figure below, neglecting the mass and moment of inertia of the lever of length L1 plus L2 and spring on straight. Okay, so basically, when I look at that problem, I see different options as a solution. Okay, so first, they say to model this as 1 degree of freedom. Is this, if you have to model this, the whole thing, is this really a single degree of freedom? How many masses do you really have? Mass of the bar and mass of the mass, no? So if you think about it, this bar can have some type of motion and this one could have also a type of motion. All right? So basically what they are telling you in this problem is to neglect the weight of the bar or the influence of the bar. Okay? But that's not really the right things to do, no? Okay, but it's just a problem. Okay, so let's see what they mean over here. So let me do the figure. I do it on my page, and then I switch to the page, and we can get it from there. So basically, it looks this a bar over here with a pin. This is L1, L2. Looks like it's some type of mass at the bottom, and there's a spring at the top, K. All right. And they say to determine the equation of motion in function of theta. Okay, so you find the equation of motion, you know what is the natural frequency. So I didn't set up the camera here. Looks like, but I did. All right, so here's the camera, okay? So basically, it looks like this is the problem. So they say basically here to neglect mass and moment of inertia of bar. Trying to zoom out a little bit so you can see the picture. Okay. Okay, so what is the thing that I told you that is the most important thing that I will be grading? Is the procedure, no? So step 1, let's do a figure and see what we get. Okay, so I'm going to do the problem probably not the way I will do it, but so basically they tell us to ignore this bar over here. That's why I do like on dash, okay? So this is the pin over here. Let's call it point O. And if we look at the forces, so this is the force in that direction. You will have a force over here that will be, let's say, Kx1. And then this mass here is given. So what are you going to have here on this mass? You will have the weight, correct? mg. All right. So this is for the forces. So if I kind of redo the same figure here. Now for the inertia effects, what type of inertia effects could you have over here? So if you look at the motion of this one, this could be, motion of this should be perpendicular, no? MA, or this will be MX double dot. Yeah, the velocity, the acceleration will be perpendicular at that point. Okay, and again, this will be point O. And I'm going to put it, even though we're going to neglect it. What could you have over here? The moment of the bar times I omega. Okay, so in this problem, they tell us to neglect also the moment of inertia. So what does that mean? That this term will be 0. Okay, so step 2 is step 1 is to do some type of figure. Step 2 is to use kinetic equations, dynamic equation. So summation of forces equals to MA, or summation of moments equals to I alpha. Okay, so from here, what type of motion is this bar with this block having? It's kind of having rotation, no? So let's see. So what is the equation that should define the rotation? Will be summation of moments. So let's see if the summation of moments should be sufficient. So let's say we take moments about point O, that should be equal to I sub O alpha. And let's say this will be positive. Oh wait, I need to put some extra stuff here, so it should be L1, L2, and they say to use it in function of theta, so I'm guessing this will be theta over here, and that angle here will be theta. Okay, so if we look at the figure, what should be the moment created by kx1? So it should be going counterclockwise, so that would be positive, no? So it should be the force kx1 times what would be the arm? L1 of what? Sine or cosine? Should be the cosine, no? So cosine theta. All right, and now what will be the arm for mg? So mg will also be created a moment. Looks like counterclockwise, so plus mg. And this time, what should be the arm? L2 sine theta. Okay, and this should be equal to what? To M A, well, this should be X double dot. Sorry, what am I doing here? Sorry for that. I was just thinking summation for the close domain. No, so wrong. So now, by definition, what is the definition of moment? Force times distance, no? So really, this is already perpendicular. So we don't have, I mean, if you want, you can break this into two components, but since this is perpendicular, what should be the moment? This times the distance, no? Yeah, so plus M, let's call this one X double dot 2, and then that distance is L2 equal to 0. All right, so let me just rewrite it because it's K x1 L1 cosine theta plus mg L2 sine theta plus m x double dot 2 L2 equal to 0. Okay, so I want to do it in detail. So basically, of this equation, I mean, they say, or I'm pretty sure they say, assume small angles. So what is the small angle assumption that we generally use? Means that sine theta will be approximately equal to theta, and that cosine theta will be approximately equal to 1. Okay? All right, so the next thing to do, if I want to break it into a procedure, but really you could do everything in one step. So now we have that equation. We might need 3 additional equations, so it will be, generally those equations will come from kinematics. Basically, we can probably do it from the figure. So in this one, x1 in function of, x1 from the figure here, in function of the figure should be equal to what? Should be equal to L1 sine theta. Okay, and if you want, here you could do it as well, but I mean, it would be more difficult to find x double dot. If you want, you could take, and if you want, you could say this is the bar, this is point O, this is A. If you want, you can call this point here P, no? Okay, but basically what are you gonna have over here? That x2, so which is this one over here, should be equal to what? I mean, if at the top we had L1 sine theta, this should be L2 sine theta, no? Okay, so with small angle assumption, what does that mean? X1 more or less equal to L1 theta, and X2 more or less equal to L2 theta, or X double dot 2 will be approximately equal to L2 theta double dot. Okay. Substituting to that equation, so substituting into, let's say, the star equation, this should be step 4, solve into star equation. This is this one here. Just rewrite it. What do we have? K x1 L1 cos theta plus m g L2 sin theta plus m x double 2 L2 equal to this. So if I substitute now for x1, we have k L1 squared, so this should be equal to 1. So this is k L1, and this is L1 squared theta, no? Multiplied by this L1 sin theta, plus mg L2 theta, so this will be theta for the small angles, plus m L2 square theta double dot equal to 0. So basically, or if you want to rewrite it, it should be equal to m L2 square theta double dot plus mg L2 plus k L1 square theta equal to 0. So this should be the equation of motion. And what would be the natural frequency? Should be the K over M, so should be mgL2 plus KL1 square divided by mL2 square. That should be the square root of that. Okay, so any question about the process? Is that the same answer that they got? I have no idea, so we can go and check. But if it's not, it doesn't matter, because what matters to me is the procedure. So I thought I had this open. Okay, so I can close this one. And then we go to this one. So it looks about the same. Okay, so guys, obviously, whoever did it with the energy method, I knew that you got the solution, no? I mean, you have to be a genius. So the way this is actually explained to you is not good, because they don't even put the Lagrange equation, no? So some of you did it and actually expanded. So I saw that you spent the time to understand what you were doing. So I gave you a lot of credit for it. Some people just copy it. So to me, that doesn't show that you understand the material, no? And at the end of the day, what's important to me is that you understand the material. That's what I need to grade, no? Know how good you can copy a solution from online or from whatever you want. All right? So, okay, now if you want personally, the way I would have solved this problem is I would have said to neglect the mass, maybe, but I would have said to keep the moment of inertia. Yeah, so if you ask me, my personal solution would have been so now let's say now, let me go to camera again. Okay, so my solution would have been, and that's why I want to tell you guys, I'm not really looking for a specific solution. I'm looking for you to follow the process to get to a solution, no? Okay, so let's say if the moment of inertia different than 0, then what would you have in this equation? So I'm not going to redo it. If you want, you can do it. You will have the same thing over here, but this will be equal to I sub naught. What? Alpha will be theta double dot. Yeah? So now what would that give you? Okay, let's say if I'm following some procedure, what would you get? Probably you would get a very similar equation to this one, but what would be the effect? You will have another term here on the theta double dot, no? Correct? That this time we take into consideration the bar. All right? So probably the equation, I'm just guessing, okay, let's put it would be an educated guess. The equation would be what? I sub naught plus m L2 square theta double dot plus the rest will stay unchanged. So probably if I had to do the problem, I would have ended up with that solution. But you see that is similar to this one, no? All right. So remember, engineering, you're not always going to end up with just one solution. You might end up with multiple solutions. And let's say if you needed to study this problem, the whole thing without doing any assumption, this problem would not be a single degree of freedom, it should be a 2 degree of freedom. correct? Because you will have the bar and the mass, no? So you will have to do what? A free body diagram for the bar. All right, so I mean, if you want to redo the figures, then you want to work it out. So if P1 is analyzed as a 2 degree of freedom, what should be your two diagrams? You will have one for the bar that will have what? Kx1. Then you will have to take into consideration the mass of the bar, no? In here, I think the trick will be to say there will be a tension connecting the bar to the mass. Yeah? And then you will have over here the other free body diagram. Just look in the inertia effects, I sub O alpha, where this will be point over here. So here, be careful. I mean, you see that, just one, I mean, I'm not going to do it, I'm just going to give you the thinking, okay? If this is a bar, what is really the ICG of the bar? So the moment of inertia of the bar about its CG, you don't know this stuff, but you can find in the book, is M L squared over 12, where L will be L1 plus L2, okay? But what will you have to do? You will have to move the I of the CG to the point of rotation. And you will do that using the power axis theorem, no? So you see, it's a lot of little things going on, no? So move 2.0 using polar axis theorem. That basically would be what? I sub dot would be ICG plus M, and L squared would be, I think would be whatever distance between the CG and point O, no? So what would that be? Would be like, whatever. The distance between the CG and point O. Okay, let me call that one capital L. So L will be distance between the CG, that could be here, and point O. Okay, so it will be what? Whatever would be the middle would be L1 plus L2 divided by 2 minus L2, no? Looks like. So it will be, where L will be L1 plus L2 divided by 2 minus L2. And you will take this one squared. So this will be the first figure for the bar, and then you will have what? Another one for the block. Like what? So you will have here the tension P. You will have here the mass of the block, and then you will have here what type of motion is this going to have? MX2 double dot, no? And following the same procedure, then you will end up what? With one equation of motion for the bar, one equation of motion for the block. Does that make sense? Okay, so that's the kind of stuff that I'm looking for. So you see that I'm not really looking for a specific solution, no? I'm looking that you follow the process, you make your own assumption, and you end up with a solution. That's what I'm looking for. Do you have any question? Let me pause. Okay, so using energy is a solution that is on the online. So since you neglect the mass of the bar, it will be no kinetic energy coming from the bar. All right, so the energy is just coming from the block at the end, and that would be 1/2 mv squared, which is x dot. And we said that the deformation of this one was L2 sine theta. So L2 sine theta is approximated by L2 theta. You square this stuff, you end up with this. Okay, so that's the only kinetic. This is really the only kinetic energy. All right, you see here, this is a kinematic relation that I did in step 3. No, okay. Now, what would be the potential energy? You have the potential energy of the spring, which is 1/2 kx1. X1 we say was L1 sine theta, becomes L1 theta, and then there is the one due to the change in height of the mass. Okay, so this L2 of 1 minus cos sine theta, what does it represent? If this is straight and this is moving up, how much did this move up? So let's say your reference is right here, no? It was straight. It's going to move up that distance. What is that distance? Is L2 minus L2 cosine theta. Okay? When you factor out, you get L2 of 1 minus cosine theta. All right? But here you need to be careful because here, and that is the, I mean, not a trick, but you cannot take the approximation of this equal basically to 1, no? Because then it will give you to 0. And the reason you cannot do that is what? Is because now, you see here is not properly done. You need to apply the Lagrange equation that we are on the note. So which is what? You need to take the derivative of this. You need to, the derivative of this in function of theta dot. All right, if you look at the notes, you have the Lagrange equation, no? You can probably go open that on the notes. So I think we did it even at the beginning. You see we had this problem here that we did in both ways. This is this way. And then we have Lagrange equation to derivation of equation, which basically I did the derivation. And this is basically what you have at the end. d dt dx dot minus di. Well, L is kinetic energy minus potential energy. So here, what x in this equation is not x on our problem is theta, no? Okay? So you need to take the derivative in function of theta dot, and this one in function of just theta, which obviously they kind of do it, but not in a very direct way. All right, so you actually take the derivative in function of theta. That's what you get. What is the derivative of theta dot? Would be theta dot. So the derivative of x squared is 2x dx. Correct? So the equation of theta dot would be theta double dot, no? Yeah? Okay? And that's why they have here, and that's what they do. You see here, this one here becomes sine, no? Sine of theta dot. Okay? But that's what I'm saying. People that copy this, I knew you were not understanding what's going on. All right? And basically then that with the same relation. Like I said before, I know how to use that, and to tell you the truth, the Lagrange equation, energy methods are really good to solve very complicated problems. Okay? So yeah, if the problem is very complicated, it's through the energy methods, it's easier. Okay, it makes it a lot easier. But for this type of problems that we have been doing, that are kind of, just to understand the material, I think it's a lot easier to use this type of approach because you don't have to make any assumption and you see exactly what it is, no? If you do the right figure, you write the equation from the figure, no? Okay? But again, it's true that to solve complicated problems, sometimes the energy method is very convenient. And we might do that at the end of the semester. Okay. You want us to do problem 3, so problem 3, I have no idea what that is. But we find out. Okay, so this is problem 2, problem 3. Oh, yeah, see, I think I looked at it the other day. So problem 3, how do they solve that one? Energy method, I think, now as well. Yeah, so you see, which is probably correct. So here in this one, they do a little more, and here instead of using, you see, they use the T plus U, because really here is not really using the Lagrange, it's using a different form of the Lagrange, which is called the principle of minimum potential energy. But I mean, you don't know this stuff, but it's not really using Lagrange here, no? It's a kind of Lagrange, but not the way we did it in class. So anyway, let's look at the figure. And this problem, I've seen it many times in textbooks, so I'm sure it's a classic problem. So I'm just going to copy the figure. And for a second, let me look at the problem statement. Let me read the problem statement, see if there's any assumption. For the system shown in the below figure, where the disk has a mass m and a moment of inertia 0, determine the equation of motion in function of theta, the natural frequency. Okay. So I'm just redoing the figure on the page here. And they ask us to find the equation of motion function of theta. Okay. So I think theta would be whatever deformation you deform, this would be the angle, no? So all right, let's do this, okay? Let's see what happens. So step 1, we need to do some type of figure. All right, figure diagram. So we're gonna have what? They don't have to do that, but let's say we move this point here to this location, okay? So we kind of, I want to assume a deformation, I kind of assume that this is moving to the right, okay? So this point, let's say it would be here, all right? So what happened to the spring forces? If you move this point here a little bit here, really should be lower, but doesn't matter. What's going to happen to this one should be, this one should be pulling in that direction, no? And then if you push it this one, so wait, if you pull, no, it's the other way around. If you pull this one's going to try to pull you back in, no? So this should be on the other direction, no? Yeah? So basically, if you move this one there, the spring is going to try to pull you back to the same location. And this one is going to do the same thing, so it's going to push you to the right. Huh. I don't like that initially, but I mean, we'll see. We follow procedure because this one we kind of cancel each other, it looks like, no? No, because when you pull this spring here to the right, what is this spring going to try to do? It's going to pull you back to the left. And this one, when you push it to the right, it's going to try to push you to the left, no? No, this one, when you push it, it's going to try to push you to the left. So this arrow is to the left. This one, you push it to the right. So yeah, so both are, so this one, so you push it to the, you push it in. Yeah, so both are going to the left, is that what I'm saying? Yeah, that's what, so what did I change at the beginning? Okay, so both are going to the left. Good, yeah, thank you. I think I had this wrong. So both of them are going in the same direction. What else can you have over here? We're going to use it, but you can have the mass of the sphere, no? And then in this one, I'm pretty sure we're going to need it since they don't mention, because they didn't say this was a smooth surface, no? So that means that this has some type of, so it should be a normal over here. And if I'm over there, should be some friction over here. So let's say the center, let's call the center point O, and this point of contact here, point P. I mean, if you took dynamics with me, I always call that point P. It's not, I don't know why, okay? Just call it P. And now what type of motion this could have? So you will have here X double dot or MA. Or this could be I alpha. Okay, so let's follow the procedure, because really let's follow the procedure. Okay, let's see what we get. So now so let's say this is point P, and let's call this point here Q. This point over here will be Q. Q. Just trying to think. All right. So it's good, because to tell the truth, the other one I kind of had a knowledge of what was the answer, no? This one, I don't know where I'm going. So it's good. That way we can just follow the procedure. So let's say we do the first one, summation of forces. Equals to MA. So what would that give you? Will give you minus KX minus KX minus the friction force equal to mx double dot. Okay, so this will give you basically minus 2kx minus f equal to mx double dot. Okay, so what I don't like about this equation is that f over there, but maybe we can save it that way. Maybe we can leave it that way. Let's see. Okay, so yeah, I think we can use that equation. So this will be the x, the acceleration at which point? At the middle of the circle. So let's say it would be x sub O double dot. Okay. All right. Now the other equation should be what? Summation of moments equals to I alpha. So here, I mean, I was going to do like, I think this is my intuition that we could solve this problem just with this one. But I want to do whatever you want. So here you have two choices now. Okay? About which point can we take the moments? About which point will you take it? You want to do it about point O? Okay, let's do it. We're going to do it about point O, okay? And then next I explain why maybe I will have done. Since I don't like this force F, what could you do? If you want to remove the effect of this force F, we could have taken the moments about point P, no? Yeah? Okay, but I mean, it's math, it should work also if we do it from point O, no? The other thing is that then we're going to have the force of the friction that I think we can solve from this equation, you see? So we'll have to substitute, no? If we take the moments about point P, then we probably don't need this equation. That would be my guess. But if you want, you can work it out later. Okay, so we do moments about point O. Then what are we going to have? So the 2kx here So this will be 2kx at point Q, no? Because how much x is going to deform here is different than what's going to deform at the middle. That's why I call this one x sub Q, x sub O. And this one will be creating a positive or negative moment. Positive, and the arm is, according to the figure, is R. Yep. Okay. So times R. Then what do we have? We have the force F, no? That will be creating a clockwise moment, so negative moment, minus F times R, no? So this is, wait, we don't know, I did a mistake. This one should be A, no? Sorry for that. This is A. This is letter A over here. Distance between O and Q is A. And now this should be minus F times R. Anything else is creating a moment here? Looks like that's all, no? So this will be equal to I sub O alpha. Okay? And this will be our equation 2. So here mentally, all right, we have two equations. And we have, what do we have? Ooh, so be careful here in this equation here. What should be this x over here? Which x should that be? Is it the same as this one? This is the arm that we call x sub q, no? You see, be careful with the notation. So here you can do that mentally, but how many unknowns do we have? F, x sub q, x sub naught, and it looks like kind of alpha. It looks like we have like 4 unknowns, no? So 4 unknowns, looks like we have 4 unknowns. We only have 2 equations, so we need to find at least 2 additional equations. I mean, we need to find 2 additional equations, but maybe by adding equation, we end up with more unknowns. So we'll find out. So we need to go now to find additional equations. Where do we find additional equations? We go to the kinematics. It's all the time the same procedure. So 3, the additional equation, they come from kinematics or geometry, which is basically the same. So this problem over here, this is a classic problem from dynamics. So every time you want to calculate the velocities or the accelerations, you need to start from a point where you know what's going on. So in this figure, at which location do we know the velocity instead of talking about acceleration? Do we know the velocity at any point? Okay, so if you think about, maybe let me use another page. That will be last page. So this is going back to dynamics. We go on this page. If you have a ball, can be a ball, can be a sphere, can be whatever you want, that is moving, okay? So let's say this is moving. And obviously, in order for this to roll, what do you need to have? Friction. Because there is no friction, it's just going to slide. Correct? All right. So it is friction, that means that it will be 1 point of contact over here. So now, what happens if you have a ball rolling, and let's say you take pictures of the ball rolling at high velocity. It's going to look, and if you put the pictures side by side, this is always going to look like, no? So This is the center, this is the center. So it will look like what? That this point here is really what? Rotating about the point of contact with the ground. So if you do this, the motion of the center of the ball should look something like that. Does that kind of make sense or no? It will look like this point here, O prime, O double prime. This will be P, P prime, P double prime. In here, it looks like point O is rotating about the point of friction. So if you put my marker here, this is point P, this is point O, and that instant will look like it's doing this. Because it's friction. If it was not friction, what will happen? First one, this ball, point O and point P will just be moving at the same velocity. Correct? Yeah? Because all this will be moving on the block. It will be no rolling, no? In order to have rotation, what do you need to have? Friction. There's no friction, you cannot do this. So what does that mean? Is that at those instants, the motion of the center, or can be the motion of point Q, will look as that it is rotating about point P. If it's rotating, what does that mean about the velocity of that point? It will be 0. That is what is known in dynamics as an instantaneous center. Remember the instantaneous center? Okay. So anyway, let's go back to here. So from kinematics, I have this problem. So okay, so just let me redo here a figure. So it will be P. This is O, and let's say this is Q. Or really Q should be Q prime. Okay. So what I'm trying to find is the first thing. So let's look at I'm just trying to find first the relation for alpha. That is, the reason I want to do it that way is because I think it's going to give a negative value. All right, so the acceleration of point O from point P is given by this relation here. Okay, so here without giving too many details, this term here is cancelled out by this one. This is dynamics. Not going to get into detail about that. If you want, I can get. This is the theta double dot. So basically, we get the acceleration of O, which is basically is just x of O 0. Hopefully, we just get one component, should be equal to what? IJK 0, 0, theta double dot of position of O with respect to P, that will be 0, R, 0. So basically, this is going to give us what? X sum naught. Sorry, X double dot sum naught, which is the one from this equation here, is equal to what? Minus R theta double dot. Equation 3. Let me look at the solution for a second. I want to make sure. You want to look at the form of the final. Do they have a theta and not this stuff? So this is basically what we have. Okay, so they tell you this is mr squared. So that everything function of theta. What is the effect of the springs in here? What is the, here we go, potential energies. A plus R theta, okay. Yeah, okay. So now, this is R, this is A, this will be theta, okay? So basically when this is moving, what will be the position of Q or Q prime in function of theta? So we know X or not, and what can you say about X sub Q should be equal to what? I mean, we could do it if you want. So let's do it, okay? Let me put the equation. So let's say we need to find the velocity of Q prime. Okay? Because after the move, it's going to be a Q prime. What would that be equal to? Would be equal to Vp plus the angular velocity, omega cross R of Q prime with respect to P. Yeah, that should work. So we know Vp here is 0 because there's friction. So this is equal to what? I j k 0, 0, omega will be theta dot. Of what? What is the position of Q prime with respect to P? What will be? What will be? How much is that going to move on X? Looks to me will be A sin theta, no? Okay, and what would be for the Y? So it's going to be a little more complete. It's going to be long. So it's going to be what? A plus R or R plus A minus A sin theta, no? Or should be, we can do it R plus A cosine theta. We can do it that way, probably it's easier. R plus A cosine theta and 0. So basically that means that VQ prime will be equal to what? So we do the velocity vector at that point should be equal to 0, 0 minus R plus A cos theta. This one minus this one, and this one be minus this one, so it should be, and this is theta dot, and A sin theta, theta dot. Okay, so the amplitude of the velocity at that point should be equal to what? A sine theta theta dot square. I mean, I'm doing the x squared plus minus r plus a cos theta theta dot square, and it should be the square root. So I want to remove the theta dot. We don't need it, so it will be a square. So we have here sine square plus cosine square. No? Once you do that, this one here, this one is square, this one is square, no? And then you have another term here that would be what? Plus r square. Yeah. So basically this would be equal to what? And here you have the theta. Okay, you have the theta dot. So it should be equal to a plus r theta dot. Okay, so now what is velocity? Distance divided by time, no? Okay, so the magnitude of this should be equal to what? So if the velocity is this, what should be x cubed? You integrate this, no? So it should be a plus r theta. No? Or if you want, I mean, I want to try to make it simple, but velocity is equal to what? Dx dt. So dx will be equal to the integral of v dt. Yeah, that's basically what I've done, no? Okay, so I think now we have everything we need. So for equations, for unknowns, we can go and solve. So step 4. Solve. Okay. So let's rewrite the 4 equations that we have. We have minus 2k x cubed minus f equal to m x double naught o. Then we have 2k x sub q times a minus f times r equal to I sub naught theta double dot, because alpha equal to theta double dot. This is our equation 1. Our equation 2. Equation 3, we have acceleration of point O is equal to minus r theta double dot. And our equation 4 is x of q equal to a plus r theta. Okay, so let's see what can we do over here. So basically, what do you want to do, guys? Solve here for f and substitute over here, or solve here for f and substitute on this one? Probably it's easier to solve here for f and substitute onto this one. So solving, so from 1, we're gonna get what? F will be equal to minus 2k x sub q minus m x double dot o. Okay, so can I do substitution now? Or this will give you what? F will be equal to minus 2k of A plus R theta. I'm substituting with this one x cubed minus M of minus R theta double dot. So it's good. Everything is in function of theta, no? Okay, or this will give you F equal minus 2k A plus R theta plus M R theta double dot. So now our last step would be to do what? Substitute this into which equation? Into equation 2, no? That should be the last step. So what do we get? So now I'm going to do 2k x cubed times A minus, let me just rewrite it, F times R equal to I sub naught theta double dot. So this will give you what? 2k of A plus R theta times A minus F, which is 2k okay, I'm going to put a bracket here. 2k of A plus R theta times the arm, which is R, equal to I sub naught theta double dot. I forgot here this term. You see that? In A, no? So I forgot this term in L. I just put this one. So let me rewrite it. So we get 2k A plus R theta A minus 2k A plus R theta plus M R theta double dot times R equal to I sub naught theta double dot. So if we carry the algebra, what do we get here? So this will be the theta. So can we factor by 2k? Let's say 2k of A plus R. This will factor by what? A minus R. Looks like, no? A minus R. And then here we're going to have equal to I sub naught theta double dot. This is a minus plus M R square theta double dot. This is a minus, no? Here's a minus. So this one is minus. When I move it to the other side, it becomes positive. And here I forgot the theta. And all these terms I forgot here the theta. That's why I was doing that. So at the end, what do we get? The equation of motion is M R squared plus I sub naught theta double dot plus 2k, and I don't know how they wrote it, but a plus r times a minus r, it should be equal to what? A squared minus r squared, no? Right? Times theta equal to 0. So is that what I get? Oh, this is the class notes. We'll make that. This is the one we need. So 2k a plus r squared. Where they get a plus r squared? Is it so? Maybe so. Here we ended up a plus r times a minus r. They ended up with a plus r squared. So we have a sign part, and this is the same that we have. Okay, I'll show you now what this time. So maybe we need to check the sign here of one of the a plus r or something, and let's check. And I'll tell you where this 2.5 is coming from. So in the problem statement, what do they tell us? That I sub naught is equal to 1/2 m squared, no? Okay. So if you do, so this term should be equal to what? Square plus 1/2 m squared should be equal to what? 3 m squared divided by 2, no? Which is what I have on the solution. Agree? So here, let's check, because the only difference we have with the solution is that this one here that I put a minus r, they have a plus r. So, I don't know, is that a plus r? What did we do over here? We factor by this one. So, I think it's minus, no? So this is our solution. What can we say? But you see what will be the difference? In this term, they will also have a plus r. We have a minus r. So maybe we need a bit of time, but basically we get the same. All right, we'll have to check maybe the sign order. But again, what's important is now the final result is the procedure, no? Okay. So do you have any question?